Async JavaScript can look simple until your code runs in the wrong order or returns promise pending instead of real data. In this video, we will solve 16 practical async await challenges that junior developers often face in interviews and real projects. Each task has a clear input, expected output, and a step-by-step explanation. We start with the foundation, creating promises, waiting for them, and adapting callback-style code to modern async and await. In real apps, data often arrives later, like from an API or database. Here we write delay value, a small function that resolves with the same value after a delay, then we call it with Alice and 500 milliseconds. Now we run the script and watch the terminal print loading first, then Alice after the promise resolves. Let's break down why this works. The promise is created immediately, but it does not resolve until setTimeout calls resolve. The await keyword waits inside main, so the second log happens only after the delayed value is ready. Now we show the better habit to keep. Put asynchronous behavior behind small functions with clear names, because the rest of your code becomes easier to read and test. This pattern is useful whenever you wait for timers, APIs, files, or database calls. For practice, change Alice to Bob and change the delay to 1000 milliseconds before running it. Predict the order of the logs. The output should still be loading first, then the resolved name. Older JavaScript code often gives results through callbacks, but interview tasks usually expect promise-based flow. Here, we keep the legacy function as it is, then create getUserPromise around it. Now we run the script and see that awaiting ID 7 gives us the user object. Let's break down the conversion. The promise constructor gives us resolve and reject. When the callback receives a user, we resolve it, and that resolved value becomes the result of await. Now we show the best way to use this pattern in a real codebase. Convert callback APIs once at the boundary, then use async and await everywhere else. That keeps your business logic cleaner and avoids mixing two async styles in every function. For practice, add validation to the callback function. If the ID is less than 1, pass an error as the first callback argument, then update main to catch that rejected promise. Now we move to failures because real async code must handle rejected promises without crashing the program. In real applications, user lookups can fail, and that should not crash the whole script. Here, findUser resolves only for ID 1 and rejects for anything else. Now we run it with ID 2 inside try and catch, so the terminal shows a friendly error message. Let's break down the result. When an awaited promise rejects, JavaScript treats it like an exception at that await line. Because that line is inside try, the catch block receives the error object and prints only its message. Now we show the safer habit. Use try and catch when a failed async operation is a normal possible outcome like missing data, network failure, or denied access. That makes the failure path visible and controlled. For practice, change the call from findUser2 to findUser1. This time the promise should resolve and the catch block should not run. Use that to compare the success path and the rejection path. Next, we look at a common interview detail. Every async function returns a promise, even when it returns a plain value. This comes up often in interviews because async looks like it returns a normal value, but it always returns a promise. Here, calculate discount returns 90 inside the function, then we log the raw result before awaiting it. Now we run the script and see the promise first, then the actual value. Let's break down the important part. The return statement gives back price times 0.9, but async automatically wraps it in a resolved promise. Await is what extracts the resolved value, so the final log prints 90. Now we show the practical rule. Await async function results unless you're intentionally passing the promise somewhere else. That keeps later code working with real values instead of promise objects. For practice, remove the async keyword from calculate discount and run the script again. The raw return value will no longer be a promise. This is a quick way to prove what async changes. Finally, for this batch, we practice controlling order when async steps must happen one after another. Some async work should not run in parallel, especially when one step depends on the previous one. In this payment example, we must validate the order before charging the card and charge before sending the receipt. Now we run the script and check that the terminal prints the 3 steps in the exact order. Let's break down the sequence. Process payment does not move to charge card until validate order resolves. Then it waits again before sending the receipt, so the printed order matches the business process. Now we show when this is the right pattern. Use sequential await when each operation needs the previous one to finish successfully. If the steps are independent, then you can consider promise all, but payment-style workflows usually need strict order. For practice, add update inventory as a fourth delayed promise. Place it after charging the card and before sending the receipt. Then verify that the terminal output follows your new workflow order. In this section, we work with async operations that can run at the same time. This is one of the most common interview areas because real apps often load several independent resources together. In a dashboard, profile, notifications, and settings are separate requests, so running them sequentially wastes time. Here we create 3 delayed async functions, start them inside one promise, all call, and then run the script to see the combined result. Let's break down why this works. The 3 function calls happen before await pauses the function, so all timers are already running. Promise all simply waits until the slowest one finishes and then gives us the results in the original array order. Now we show the best pattern to remember: use promise all when every operation is required and none of them depends on another one. This keeps the code simple and avoids unnecessary waiting. For practice, add one more independent request, create fetch permissions, give it its own delay, include it in promise all, and confirm that the total wait still follows the slowest request. In a checkout flow, a missing dependency can make the whole operation unusable. Here we run 3 service calls together, but the inventory service rejects, so now we run the script and watch what promise all sends to catch. Let's break down the result. Promise all does not wait to build a partial success object. Once inventory rejects, the whole await throws and execution jumps straight to catch. Now we show the best way to decide when this pattern fits. Choose promise all when one failed dependency means the final result should not exist. That makes the failure clear and prevents the app from pretending the operation succeeded. For practice, make the pricing call reject after 100 milliseconds. Run it again and check which error message reaches catch first. A dashboard can still be useful if one widget API is down. Here we load 3 widgets with promise all settled, split fulfilled values from rejected reasons, and now we run the script to see both groups. Let's break down why there is no catch block here. Promise all settled waits for every promise to finish and returns objects with a status field. That lets us decide how to display successes and failures instead of stopping everything. Now we show the best case for this pattern. Use promise all settled when partial data is valuable, like dashboards, reports, recommendations, or optional widgets. The user gets what is available and the app can still show which parts failed. For practice, add a 4th widget that also rejects. Then make the failed section print both error messages without changing the rest of the flow. Now we move from waiting for everything to taking the first useful result. Promise arrays is helpful when speed matters more than collecting every answer. For downloads, you might ask multiple mirror servers and continue with whichever answers first. Here we simulate 3 servers with different delays, race them, and now we run the script to see the fastest one. Let's break down the behavior. Promiser, race does not care about the order in the array after everything starts. It cares about which promise settles first, and in this setup, the 250 millisecond server wins. Now we show when this is the best tool. Use promise erase when one result is enough, like choosing a fast mirror, enforcing a timeout, or accepting the first cache response. Do not use it when you need every result. For practice, change mirror C so it rejects after 100 milliseconds. Wrap the race and try and catch, then observe that the first rejection can win the race too. A backend request that never finishes can block a user flow for too long. Here we create a slow request, wrap it with a timeout using promise erase, and now we run the script with a 1-second request and a 300 millisecond limit. Let's break down the result. The real request needs 1000 milliseconds, but the timeout rejects after 300 milliseconds. Because promise erase uses the first settled promise, the timeout error reaches catch first. Now we show the best habit for real systems. Put explicit time limits around external calls so the app can show an error, retry, or fall back instead of waiting forever. This is especially important for network requests and service-to-service calls. For practice, change the slow request delay from 1000 milliseconds to 200 milliseconds. Run it again and confirm that the successful request result prints before the timeout fires. In this section, we practice async code that survives temporary failures. These patterns come up a lot when you call APIs, queues, databases, or any service that can fail for a moment and then recover. In real projects, a network request may fail because of a short timeout or a temporary server issue. Here we write a small retry helper that calls an async function up to 3 times. The request fails twice, then succeeds. So now we run the script and watch the attempts. Let's break down why this works. The helper awaits the operation inside a try block, so a successful result returns immediately. When the operation throws, the catch block logs the failure, and the loop gives it another chance unless we already used every attempt. Now we show the production rule for this pattern. Always put a clear limit on retries. This is better because endless retry loops can make outages worse and make debugging harder. Clear logs also tell you which attempt failed. For practice, change the mock request so it succeeds only on the 4th call, then pass 4 attempts into retry and make sure the terminal shows 3 failed attempts before the final success. Simple retries are useful, but calling the same failing API immediately can make the problem worse. Here we add exponential backoff, so every retry waits a little longer. The mock API fails 3 times, then recovers, and now we run the script to see the growing waits. Let's break down the algorithm. The first failure waits 1 base delay, the second waits double, and the third waits double again. Because the 4th call succeeds, the helper returns the result and stops retrying. Now we show the best practice for retries against external systems. Use backoff so your app gives the remote service time to recover. In real systems, you would often add jitter too. So many clients do not retry at the exact same moment. For a quick variation, make the API always fail and keep 4 attempts. Your goal is to confirm that the helper logs 3 wait messages and then prints the final failure from the caller. Now we move from retrying one operation to controlling many operations. This is important when you have a large list of async jobs but only want a few active at the same time. Uploading many files with promise all can start everything at once, which may hit rate limits or overload the client. Here we build a small concurrency pool with 2 workers. Now we run 5 delayed upload tasks and check that only 2 are active at the same time. Let's break down the pool. Each worker takes the next available task index, awaits that task, and then takes another one. The results array uses the original index, so even though jobs finish in a different order, the final result list stays ordered. Now we show the practical rule for this pattern. Limit concurrency whenever each job uses a real resource. This keeps APIs, file systems, and queues stable while still letting you do useful work in parallel. For practice, change the limit to 3 and run the code again. Watch the start lines carefully. 3 uploads may begin immediately, but the results should still print in the original file order. The final section focuses on async mistakes that look innocent in interviews. These are not syntax errors. They are logic bugs caused by how arrays and promises interact. A common interview trap is transforming IDs into data with an async map callback. This looks like it should return product objects, but map does not wait for async work. Let's run the broken version and see what actually gets logged. Let's explain the wrong result. An async function always returns a promise right away. So map finishes immediately with an array of promises before the product data has resolved. Now we fix it by separating the promise list from the resolved result list. Promise all waits until every fetch finishes, and then gives us the product objects. Let's run the fixed version and compare the output. Now we show the best practice for async mapping. If every item can run in parallel, map to promises and await promise all. If order and timing must be strictly sequential, use a for-of loop instead. This bug appears when we send emails and need to know when all of them are finished. The code puts a wait inside for each, but for each does not care about the return promises. Let's run it, and notice that done appears too early. Let's break down the timing. For each calls the async callback for each user, but it does not collect or await those promises. The main function reaches console.log immediately, so the done message is not a reliable completion signal. Now we fix it with a for-of loop. This version awaits each email before moving to the next one. So done prints only after all sends are complete. Let's run the corrected code. Now we show the best practice for async loops. Use for-of with await when each operation must finish before the next one starts. Use promise all when the operations are independent and can safely run in parallel. In this final section, we combine several async patterns into one realistic workflow. This is the kind of task interviewers use to check whether you can orchestrate promises, not just await one function. In real checkout code, one async function is rarely enough. We need to validate the cart, load price and discount data, protect the workflow from slow services, and then return one final object. Let's write build checkout summary and now run the script to see the full pipeline in action. Let's break down why this result is correct. Validation runs first, so bad input stops early. After that, price and discount run in parallel, and the timeout wraps the whole fetch phase, so the workflow either gets both values or fails clearly. Now we show the best practice. Keep each async operation small, but keep the orchestration readable. This is better than hiding everything inside one huge promise chain because interviews and production bugs both require you to explain where validation, parallel work, timeout control, and error handling happen. Try this variation on your own. Make the discount service slower than the timeout, for example 700 milliseconds, and watch the workflow fail. Then choose a real strategy. Increase the timeout, retry the service, or continue with a zero discount fallback. Now you have practiced the most important async JavaScript patterns through real coding challenges. If this helped you, like the video, subscribe to Dev Level Up, and write in the comments what JavaScript topic or challenge format you want next.